Welcome to Buckeye Turf Podcast. My name is Carl Danneberger, Professor of Turfgrass Science at The Ohio State University. The topic of this podcast is managing salt-affected turfgrass sites. Water high in salts can occur from local water sources and increasingly from effluent water use. Salt-affected turf sites drain poorly or have low infiltration rates due to soil structure degradation. Salinity also negatively influences plant health by impacting water and nutrient uptake and reducing stress tolerances. We will look at managing these sites in this presentation, from chemical treatment of the irrigation water and also from management practice that can help alleviate and correct soil conditions. For now, we will focus on the irrigation water because, as previously mentioned in the podcast on water quality and salinity, as the water is, so then shall be the soil. There are two types of chemical treatments. The first is gypsum injection. Gypsum, or calcium sulfate, is used to displace sodium on the soil exchange sites and can be applied directly also to the soil. In a fine particle form, gypsum can be injected into the irrigation water to increase the electrical conductivity of that water, which will influence the calcium to sodium ratio. And by doing this, you're lowering the sodium absorption ratio. The photograph here is showing a worker getting ready to place gypsum into the injector. The second means of chemical treatment of the irrigation water is through acid injection. This can be done either directly into the irrigation water lines, as this diagram shows, or through a sulfurous generator, often called a sulfur burner. In this system, sulfur is burned at a high temperature, producing a sulfurous gas that, once combined with water, in this case from the irrigation pond, will produce sulfuric acid. In acid injection, sulfuric acid is added to the irrigation water using a product like urea sulfuric acid. While, as mentioned previously, in the sulfur burners, the sulfur is burned at a high temperature to form sulfuric acid. The sulfuric acid reacts with the high levels of bicarbonates and carbonates, evolving the bicarbonates off as carbon dioxide and water. Acid injection does not directly affect the sodium. 4 situations exist where the potential for irrigation water treatment may be warranted. These situations are listed here and will be covered individually. These situations are described in an article entitled "Treating the Cause, Not the Symptoms," authored by University of Georgia researchers. This paper will be referenced at the end of the podcast. The first situation is where sodium is high and the bicarbonates and carbonate level is low. The actual values associated with a high or low relative measurement of these were discussed in a previous podcast on water quality and salinity. In this situation, sodium is present on the soil exchange sites, which is reflected by a high SAR, which is the sodium absorption ratio. In this situation, irrigation water treatment is an option but not required. If an injection treatment is used, fine particle gypsum could be used, or some other soluble calcium source like calcium chloride. If acid injection was to be used, we would need to make a lime application, so once the water hits the turf, the sulfate would react with the calcium to produce gypsum. You still want calcium in a soluble form to replace the sodium and then leach the sodium out of the root zone. In most cases, making gypsum applications directly to the turf would be effective in most situations. The second situation, where sodium in the water is high to moderate with high bicarbonates and carbonates. In this case, irrigation water treatment would most likely be necessary. In this scenario, the high levels of bicarbonates and carbonates will react with any calcium or magnesium in the soil, forming an insoluble lime product. Without soluble calcium or magnesium present, sodium cannot be replaced. Thus, any applications of gypsum are compromised. Acid injection, as previously mentioned, would evolve the carbonates off as carbon dioxide in water, allowing the calcium to remain soluble. These cations then could replace the sodium on the soil exchange sites. The third scenario is ultra-pure water, which is most often associated with mountain snow melts. But in some instances, groundwater may also be pure. In these cases, the electrical conductivity of the water is low, normally less than 0.5, with sodium being present. What we want to do is raise the electrical conductivity of the water by adding ions like calcium and magnesium to counteract any sodium effects and improve soil structure. This slide just summarizes what we have previously said about ultra-pure water. Usually the impact occurs within the top inch or so of the soil surface. Light frequent applications of gypsum would be recommended in this case, while irrigation water treatment would not be necessary. The last situation occurs when calcium or magnesium levels are high, combined with high bicarbonate and carbonates. The result is the combination of these cations and the bicarbonates and carbonates. They react and precipitate out as lime, usually causing a crusting on the soil surface. This white precipitate is called calcite if it forms from the precipitation by the application of irrigation water. If the calcite results in the sealing of the soil surface by filling in pores, water infiltration is greatly reduced. Although you could treat the irrigation water, management practices like coring and spiking to break any type of calcite layer would probably be more effective. Besides water treatments, management practices are critical to managing salt-affected sites. Chemical water treatments, if installed, does not mean management practices are no longer necessary. Two cultural or mechanical practices that are important are aerification or coring and sand top dressing. Spring is the most important time to core cultivate turf sites that are using salty water or sources like effluent water. Coring helps provide a healthier environment of turf growth going into the summer and is an important practice when leaching sodium through the root zone. Given the negative impact of effluent water on soil structure and properties, as a general rule you need an average of 3 extra corings a year on putting greens, and on fairways an additional 2 corings would be recommended. If allowable, a deep tine coring is recommended during the spring and if possible in the fall, to allow for gypsum applications to be moved further down into the root zone. Unfortunately, deep tine aerification is time-consuming and expensive, especially on fairways. Although not a requirement, sand top dressing effluent or poor water sites can potentially improve water infiltration and provide a firmer year-round playing surface. It is also especially important when leaching practices are done to move salts through the soil profile. Irrigation practices need to focus on keeping total soluble salts moving downward. For this reason, light frequent irrigation is not recommended because surface salt buildup is rapid. Capillary action can cause salts to rise from the subsurface into the root zone, and during the summer, turf grasses, especially like cool season grasses, are very susceptible to salt injury. If light frequent irrigation is needed due to shallow root system, frequent leaching will be required. In the case of USGA constructed greens or athletic fields, flushing the perched water table may be necessary too. Continuous slow irrigation through cycles, referred to as pulse irrigation, is better than ponding or periodic heavy leaching to remove total soluble salts from the root zone. Pulse irrigation as a general rule means applying 0.2 to 0.4 of an inch of water per application with an interval of 2 to 4 hours cycle. For loams, this is a 2 to 4 hours period. For clays, that interval may be 3 to 6 hours. The principle behind pulse irrigation is to have water flow through the soil as unsaturated flow, which moves in a more uniform downward motion and occurs through the micropores. Ponding or heavy continuous watering is saturated flow, which occurs mainly through larger macropores, resulting in inadequate leaching of the micropores. Proper selection of the turfgrass species is important consideration when managing salt-affected sites. This chart gives a soil electrical conductivity range for cool season grasses. Variation does exist among species for both or all cool season turf grasses. Although some turf grasses like Poa annua are sensitive in controlled studies, this grass in particular can adapt to salty air conditions found on golf courses along northern coastal regions. Warm season turf grasses tend to be more tolerant of salt-affected sites, and these include Bermuda grass, although there are variety differences, and seashore paspalum, which is tolerant to high salt levels. It is important to note that even a turfgrass species possesses a high degree of salt tolerance. If management practices are not in place to prevent degradation of the soil structure, these grasses too will struggle and have a difficult time. This concludes this podcast on managing salt-affected turfgrass sites.